Chris introduce himself and the project he's working on with Kyle. So thanks again for coming down, Chris.
All right, no problem. Thank you. So I'm in Missoula. I'm the Science and Operations Officer, or SOO, or SOO. All the offices that have SOO. I've been in the Weather Service since 1993. Done a lot of fire weather, moved around quite a bit. Boise, Salt Lake, Missoula, obviously, and Medford, Oregon. A lot of mountain meteorology. Before that, University of Utah. There's a few of us U grads around. Graduated in 1993 from there. And Doug mentioned the Avalanche Review over on the table. The first one of those I ever saw was in the employee dining room of the Alta Lodge, a long time ago. And it's looking good this year. It's brand new. It's like a new magazine this year. It's really nice. You can actually see the pictures, see the avalanche. Okay, let's get into this. I was looking at this, and Jamie was talking about scale. That's what I'm going to talk about a lot too, scale and resolution. I was looking at this picture I took of the crazy mountains a few years ago, that big mountain wave lenticular cloud on the east side of that. And I think maybe what's going on here is you have a mountain wave causing that big cloud on one scale, but maybe on a smaller scale, maybe the crazy mountains are causing this chunk to be sort of carved out right there with some downsloping coming off the crazies, because the crazies are a smaller scale range than the big picture of the Rocky Mountain front. So that might be an example from the real world. So I was going to talk about resolution, which helps us as we get down to our individual mountain ranges where we're living and trying to forecast. The WRF environmental modeling system, which is what we use to downscale and do numerical weather prediction at high resolution. Things the WRF does well, things it doesn't do well. It's always a trade-off. You're trading off one thing, you realize it doesn't do this that well, but you live with it because it does something else well for you, like the winds. It does a good job of local winds. And how we generate real specific point guidance. One of the reasons we're doing that is to support Kyle. He's working here at MSU and working with the Swiss snowpack model, which is a one-dimensional model of snowpack, and so that requires a very specific forecast for a point. We also do the same thing for our airports that we're responsible for forecasting for, and if there's a big fire, we're going to support that fire operations with point data. Flathead Lake is a place we concentrate on, so we look at individual forecasts for that area. So it's about resolution. We have our global models, global weather models that are relatively low resolution. This is an example of an experimental model, which uses, it's like a soccer ball technique to describe the terrain and the weather around the whole globe. It has each one of those little tiles is like a soccer ball, and they all fit together. Good thing about this is it handles the polar regions really well because you don't have projection issues because every single tile is the same size across the whole globe. So if you're running a climate model, or you want to run it out 100 years, you're going to use a model that's low resolution because it's all about computational expense. You can actually run it over a weekend out for 100 years because it's only resolving the really big picture things. The big ocean currents, the big ocean temperature changes, the big mountain ranges. But if you come down to the small scale, these are actually the domains we use for this winter, supporting Kyle and our work out of Missoula. Here we have a 9-kilometer box, 9-kilometer grid point. So there's a grid point every 9 kilometers within that box, the outer box. The inner box is 3 kilometers, so there's a grid point every 3 kilometers in here, centered on Missoula. And we use a large-scale model, the global forecast system in our case, to initialize the outer boundary conditions of that 9-kilometer grid, and then we nest it on down to 3 kilometers. And I can generate a 72-hour forecast at 3 kilometers over this whole domain, so it covers my whole forecast area, in about 6 hours of wall clock time. On a computer, a pretty expensive computer. It's not just a regular computer. It's a couple $1,000, $3,000 computer, but it's something you could easily build. So just taking a look at terrain, this is some of the data we get into our AWIP system at work with the National Weather Service. It's a 4-panel. In the upper left, we have the European Community model. It's actually a very good model. It runs at a pretty high resolution over the entire globe, but they thin the data. They give us a much lower resolution data set that flows into our office to look at. So if you look at topography for that lower resolution data set, you can barely even resolve the Rocky Mountains. This doesn't look anything like we know Glacier Park really looks like. And the Yellowstone Plateau is just this huge blob of high terrain. It's not resolving any individual details. As you come down in scale to the 3-kilometer domain, it looks like we're doing a lot better. We're seeing individual individual valleys like the Paradise Valley, Missoula, Bitterroot valleys, things like that. Much better terrain depiction of the Rocky Mountains. If you look at the topography really closely here, this would indicate that Lookout Pass is lower than Missoula. And we know that's not the case. So you have to expect that the weather that's depicted on this low resolution grid is going to be imperfect. You always have to be thinking, what's the background of this data that I'm looking at now? Is it a high resolution model or is it a low resolution model? This here is the global forecast system. It's actually about a 13-kilometer global model, but we get the data at 20 kilometers. So it's actually smoothed out some before we get it at the National Weather Service. This here is the 12-kilometer NAM. And Jamie showed some images from the NAM. And that's what the topography looks like on our system at 12 kilometers. So what about precipitation? Same 4-panel, same models. So what we have here is a light northerly flow. This is 700 millibars near 10,000 feet, about 10 to 20 knots of northerly flow. The EC, again with that low resolution terrain, is producing more precipitation over the high terrain and less in the valleys, but it's still just big blobs of rain and snow. There's no detail to it. It's really only going to help you with timing, maybe 4, 5, 6, 7 days out. It's going to help you with timing about a snow event, but not the real details where the front ranges, the Rocky Mountain front's going to get more snow than north central Idaho or something like that. You have to come down in scale to these higher resolution models to really see the distribution much better. So this is what the domain looks like at 3 kilometers. And I pointed out just a couple of the major landmarks, but so if you think of 3 kilometers compared to those low resolution models, this is much better. This is showing individual valleys and mountains, so we're good to go. But if you look in detail, the Bridger Range is still, it's not really showing all the detail that's actually there. And if I zoom in on it, and I've chosen the latitude, longitude right here on the upper left corner that we're using for Kyle's work for this winter, 2015, 2016, now the Bridger Range doesn't look so well resolved. So even though it's a high resolution model at 3 kilometers, it's still a challenge. It's still not perfect, especially if you go to the real world. Obviously, this is not anything like that. But it's still better than having a low resolution model that's we can only look at every 6 to 12 hour time steps. We have our local model in hourly or even sub-hourly time steps. So that can help resolve timing of systems. So anybody can run the WRF EMS. It's a weather research forecast model, environmental modeling system. It can be downloaded for free and it kind of installs itself. Then you have to go through the configuration and turn things on and off as the way you want to run it. For example, we run with no cumulus parameterizations because we have high resolution grids. So we're not trying to gloss over the cumulus production of precipitation. We're trying to actually let the model resolve individual cumulus and thunderstorms and things like that. That's just an example of one thing that we've done specifically. There's also different ways to treat the precipitation, and they can make a big difference in how much precipitation you get, especially over mountains. So we've actually played around with that a little bit in the last couple of years. For people who live near a coast, they can get real-time sea surface temperatures from satellite data. And so every day when they're doing their model runs, their model will reach out to a server somewhere and pull down the sea surface temperatures, and that's very valuable if they're trying to resolve sea breeze fronts and things like that, or weather systems that are an issue with ocean temperatures. We don't worry about that in Montana. The model does resolve Flathead Lake quite well, and it actually handles the surface temperatures pretty well, surprisingly well. The way we're running the model this year, we rebuilt the modeling system over last summer. We're using the GFS latest version. It's on 0.25 degree globally, which is about 27 kilometer resolution. We're using that to initialize the system and nudge the outer boundaries of our nests through the whole run that we do. And then we let the high resolution model do everything, do all the downscaling from there on in to the inner part of the domain. And we're doing a bunch of post-processing for different types of data. Some of it I post to the internet, some of it is kept in-house. Our meteorologists look at it. The main thing that we really utilize out of this operationally is the wind and the precipitation. One thing we can do is this BuffKit system allows us to generate profile data, so up through the atmosphere, in a small file that we can post to the internet, and then somebody can go grab that file and look in great detail at specific points. And we'll do that, for example, if we have an incident meteorologist come into our area to handle an incident, fire weather or hazmat or something going on, we can rapidly set up a BuffKit point for them and say, here you go, here's your files, and they can use those in their forecasting. We're also generating snowpack files, which is the Swiss modeling system that Kyle is going to talk about. And I've worked a little bit with Eric up in the Flathead, sending some data up to Eric at times. And I don't know, Eric, if you use the BuffKit data at all.
Yeah, we do.
Okay, the direct model output. I'll show you an example of that here in just a minute. So what does the local model do well? This is from last year's version we ran in support of Kyle's work over the Bridger Range. And this is a 2 kilometer domain. Each one of these little dots is every 2 kilometers. So this is an image of surface temperature in Fahrenheit. And it basically looks like a topographical map. Cooler in the mountains, warmer in the valleys. There's a highway. The yellow is highways. It's kind of a crude map. But there's at least two things that are non-topographical that stand out on there. And that's these urban heat islands. So even though this is a model with a lot of assumptions built in, and we're saying, you know, it does okay, but it doesn't resolve the Bridger Range that well. We'd like it to be even better. It's pretty amazing that it actually captures the fact that there's a big city, there's a big town here. For Montana, it's a pretty big town or community. And this, I believe, would be Belgrade. So that's coming from the land use data that comes with the model. The model, there's a land use file which indicates where it's forest, where it's water, where it's agricultural land, where it's city. And that's actually driving the surface temperatures in this model, which I was kind of surprised to see. Another thing that it can do well at times is lake effect snow. This is Flathead Lake, northwest Montana. Yellow is the highway going around the lake. And we had a lake effect snow event. We had about 10 inches of snow was reported right in this area just overnight by a spotter. We had no idea it was occurring because the radar beam overshoots this area completely. Our radar is at 8,000 feet, so it starts off above most of the snow processes, especially when you have a very localized precipitation event like this. The radar was just overshooting it. Couldn't see it on radar. You couldn't see anything on satellite because it was cold. It was down around 10 degrees, and the clouds were the same temperature as the ground, basically, so you couldn't tell that it was snowing. We got a call in the morning, 10 inches of snow, since they went to bed, and just out of nowhere. So I modeled it down to 2 kilometers. I nested it down to 2 kilometers, and I was shocked that the model actually nailed it. I tried it with using the NAN to initialize our local model and downscale, and it didn't work at all. It had lake effect snow, but it had it up here. And there was a reason for that, which had to do with, it had a whole bunch of snow and ice down here. It didn't work out. But the GFS-based forecast downscale to 2 kilometers worked very well. And part of that reason is that the model actually has a pretty good depiction of the lake. The blue outline is the lake again. These light blue contours are temperature in Fahrenheit. This is a 20-degree contour in Fahrenheit. And the lake is about 20 degrees air temperature, 2 meters above the lake in the model. But the surrounding land is 12 degrees, 16 degrees, and even colder up here on top of the northern Mission Mountain Range. It's about 8 degrees Fahrenheit right there. So because the lake was indicated to be warmer, the model knew that it was an open lake with basically 32-degree water. That drove a circulation, and the white vectors indicate a north wind coming down across the north part of the lake, the south wind coming up across the southern part of the lake, and then a convergence zone right in the middle where those winds are meeting. And where low-level winds meet like that cause a convergence zone. The air's got to rise, you get the cooling, you get the precipitation. That generated the lake effect snow right in this area. So this is an example of something these local models can do really well. Winds. We use these all the time for the winds. This is the Glacier Park region. The white outline is Glacier Park, Kalispell, Flathead Valley is right in here. We use the local model for the winds over Flathead Lake a lot. It really helps. It shows that the winds tend to be more southeast rather than southwest. The other models, the operational models we get from the National Weather Service, always show southwest winds. This local model, when you downscale it, there's something about the terrain. Those winds actually are much more southeasterly and stronger on the east side of the lake. Right around here. And then look at the turning of the wind up into the mountains. Lots of detailed flow patterns. And then on the east side of the range, look at the Rocky Mountain front. 46 knot sustained winds on the lee side in the Chinook zone of the Rocky Mountain front. So the local model is handling that quite well. That's another good thing about it. This is Bozeman area down here. Bozeman's right here. Light winds in the valley, stronger winds across the ridge. And even stronger winds in the Livingston area, of course. So these models are pretty sophisticated. They can resolve that kind of phenomenon. Here's an example of precipitation, another thing we look at a lot. On this day, a couple weeks ago, a cold front had swept across the domain during the day. This is 21Z, which is 3 p.m. daylight time. This is the cold front right here. There was lightning with this cold front as it swept across the Bozeman area in southwest Montana. But well to the west of the cold front, all these different mountain ranges are still picking up precipitation because you get those cap clouds on top of the mountain ranges. And the model was resolving that. It's also showing the upslope area into north central Idaho. This area gets 60 plus inches of rain a year. There's a rainforest in here, cedar trees, and this is why. It's also showing the north-south oriented mountain ranges very well up here. The big winner on this day was the Mission Mountains. Upslope flow, orographic, terrain fixed, precipitation occurring well away from the cold front. Also convection. These models are allowed to resolve thunderstorms and actually allow them to develop and decay instead of trying to parameterize that motion in the atmosphere, which is what the big scale models do. And they can actually generate patterns that look like real thunderstorms. This is a case from 1998, and I've recently been doing a study where I've been taking all the 1 inch or larger hail days in my area and downscaling, rerunning the data using a canned data set, the model data, and then downscaling it to 3 kilometers. Same system we use operationally, just to see what it looked like. And on this day, Missoula had tennis ball of hail come through. Did a lot of damage. And the model, sure enough, showed these big cells, high reflectivity, just like you would look on the radar in the summertime. One thing about the radar and the beam blockage issues and the decisions that were made about where you put the radars, a lot of the motivation for the radars was large hail, tornadoes, damaging winds, flash floods. And those storms punch up so high that even with the beam blockage issues, you can still track them. You know, you can track big thunderstorms over the Bozeman area. But in the winter, when all your precipitation processes are much lower and more subtle, that's when the beam blockage issues are really a problem. So these convection allowing models are a new thing. This is an example of an operational model called the HRR, High Resolution Rapid Refresh. And this is the same thing. It's allowing the convection to occur. And we're seeing structures that you never used to see in models. You know, you'd never see that with that low resolution European center model data or the GFS model data. You're seeing these cellular structures and lines and fronts, and so they won't get the model. They won't get the thunderstorms exactly in the right place at exactly the right time, but they'll give you an idea of whether you're looking at a tornado type storm, large hail tornadoes, or a damaging wind type storm. So that's the new thing. All right, back to our modeling system this year. One of the things we're doing for post-processing is generating these human-readable text files. It's direct model output for a single point. This particular point is for Bridger Bowl. Kyle's going to talk more about the point and the forecast this year. This area here is precipitation and snowfall. We do generate these for Noisy Basin and Whitefish and all our important airports, Flathead Lake, some other snow tells. In this case, we had a cold front. This would have been yesterday morning. The cold front came through 30, 40, gust 50 up on the ridge at Bridger, and Kyle told me they got 9 or 10 inches of snow, and that's exactly what this indicated. Here's 8 inches, 9 inches, 10 inches by 1300 yesterday afternoon. So it started, the model said it was going to start at 7 p.m. the night before, 1900 local, ending yesterday afternoon as the wind hit and the storm blew out to the plains. So that's one type of post-processing that I'm doing. We're also generating those buff kit soundings. One of the reasons we use buff kit is if I give the modeling system a latitude, longitude, it will choose the nearest grid point, and then I can figure out it'll tell me what the XY position is on the grid and the latitude, longitude. So then I can go in and look, well, how close is that to the snow tell that I'm trying to forecast for, or for the snow study plot? And that's what we did. This is an example for Noisy Basin. Last year, the precipitation forecasts for Noisy Basin were off the scale. They were huge, way too high. We changed our grid over the summer, and they're much better this year. But through the process of dialing in on where we're going to forecast for, this is the lat long for the Noisy Basin snow tell, and this is the wharf point that we use for this winter. Quite a bit lower elevation off to the west on the big westerly slope of that mountain range in the real world. At 3 kilometers, this would be a lot smoother. So I thought, well, maybe that's not the best. Maybe I should move this point, try to get closer to something up at this elevation. So I have a way I can just move the XY point one spot, move it north, move it east, and run some code and get that same model output like this. So I tried that, and the precipitation just blew up. Produced 5 times as much precip as it did for this point. I moved it up here somewhere. And then I tried over here, and then I tried over here, and they all were way too much precipitation. So I just put it back there and just left it for the rest of the winter. And this was what actually resulted. This is the whole winter since 1st of December. Blue is the model precipitation over the whole winter up through the end of March. red is the observed precipitation in centimeters. So I thought that was good. That was good this year, much better. There could be other issues though with precipitation. Here's another spot. I did the same thing. Actually, I didn't play around with this point. This is where this is latitude and longitude indicator for Stewart Mountain, which is in the Rattlesnake Mountains, just north of Missoula. It's a strange place to me for a snow tell. I wish Lucas was still here to verify that's where it is, because it's way up on a ridge. Seems like it'd be very wind exposed. Normally they put this.
It's in the trees.
Is it? But is it up there on that ridge?
It's down off the ridge in the trees.
Okay. This is the point that I use for the wharf. It's pretty similar. It's down a little ways off from the. It's down a little ways from where the snow tell is indicated to be, but it's still right up there. It was the highest point that we looked at real closely this whole winter. It's 7,700 feet, I think. But the way the precipitation came out, the model was a lot higher than what was observed. So I'm wondering if there's any chance that got bridged over with snow, that sensor up there on that snow tell. That's why I was asking Lucas about that earlier. So there's caveats to this. You know, it's hard to tell. I've never been to that snow tell site myself. We also ran a little past, which is nice because we can just get out of the truck and walk over to it and look at it. But there were so many problems with Lolo Pass snow tell this year with the transmission problems and issues that I didn't try to do a data dump on it. Finally, the last thing I did for verification just yesterday morning, for Stewart Mountain and for Whitefish Summit, I thought I'd look at something besides precip. So I looked at temperature. I sampled 4 hours per day, kind of randomly, but I stayed away from the first hour of each model run because there can be a little bit of a spin-up issue with the models. From December 1st through early April, it was almost 1,000 total points that went into this verification. And mean absolute error was 2.4 degrees C for Stewart, bias of minus 2.3, so the model was a little on the cold side for that point compared to the observation. Whitefish Summit, I have another spot that I've been tracking. Mean absolute error was 2 degrees C with a bias, very small cold bias, 0.5 C. And that's all I had. Any questions? Yep, Jamie?
Do you think the bias in the preset for the model tends to be on the higher side when there's errors, or?
I think that if you look at a mountain range, it's too high on the top and it's too low in the valleys. These high resolution models in general.
Yeah.
I also think they over forecast the downslope windstorms in the lee of the mountains. If you try to, we've set up objective things where we monitor a certain point and have it alert forecasters. The model's producing downslope windstorm, and those alerts are going off all the time. They over forecast that compared to reality. It'll happen 1 in 10 times that the model says it's going to happen. But with the precip, I think they overdo the high end and they underdo the low end. There's too much downsloping, too much rain shadow effect in the valleys, and too much orographic enhancement at the top, I think. Yes?
And I was curious on the lake effect storm on the missions. At what elevation that 10 inches occurred at? Maybe I missed it.
Right down by the lake.
Oh.
Yeah, just right off of the highway that goes up the east side. Yes?
You said the post-processing data is posted to the internet. What are the links? Can you get to it?
You know, the only thing it's really, it's not anything like maps. There's no maps or anything like that. It's really just technical stuff. I know that the direct model output stuff has been shared with the Avalanche Center here, and I believe the Ski Patrol at Bridger. And then obviously I've shared some stuff with Eric, but he's welcome to spread it around. I have no problem with that. But all I really post are the sounding data, which is the upper level data. I don't have the links on me right now. My email is very simple though. It's just chris.gibson@noaa.gov, NOAA.gov. If you'd like to email me, I can help you out with some links.
Thank you.
Okay. Sometimes the model doesn't run, maybe the internet's down, it crashes, it's not supported operationally, it's 24/7. Yep, Eric?
So the 3K tends to handle the lake effect pretty well, at least on that example. Do you think it handles it well enough for the noisy basin point? Because there's been instances like this past winter where 3.2 inches in 24 hours of sleet.
Yeah.
And the point model is certainly underestimated during that storm. So I was curious if you had any.
I don't know, but you know what I'd really like to do? Would be to do a parallel run every day with no lake.
Yeah.
Because I'm not convinced the noisy basin is tremendously impacted by the lake. Because it's pretty far away, really, and it would have to be just the right flow and just the right stability, because lake effect's very dependent on the stability, low-level stability. So that's one of the nice things about these models. You can play around with stuff like that. Like if I wanted to study that lake effect event, we could run it again with no lake, just have it be a flat plain. We could run it with no mountains, but the lake's still in there, and see what that does, things like that. But with noisy basin, a lot of the big precipitation events I've seen have been atmospheric river events where there was just a tremendous amount of moisture in the jet stream. Like the December, I call it the Pearl Harbor storm, the December 7th event we had.
Yeah.
That was the single wettest day in Portland history. That was a once in 30-year atmospheric river event. I've also seen noisy basin and some of the other mountains up there get hammered by northwest flow with an atmospheric river, where it was a Pineapple Express that went up over a ridge and came down in northwest flow. And very high density snow and very high amounts of precipitation occurred at the higher elevations, but there was 30 inches of snow at Columbia Falls down in the valley floor because it was so much cold air down low. But aloft it warmed up. So that was a northwest flow, heavy precipitation event for noisy basin. So I don't think the lake would have been involved at all with that. So I don't know. Anything else? Okay, thank you.